Okay. All right. This is an introduction to zero net carbon design on behalf of the Central California Regional Energy Network. And this is for anybody who's new to the CCR REN or rural REN. It was approved by the California Public Utilities Commission last fall, so it's just a year old. And it's providing programs for a really super large region. It's managed through the County of San Luis Obispo as the lead administrator, and their specific programs. So here are all the partners in the territory. So you can kind of see the three main categories here and the partners of the COGs and counties. The 6 programs that they're providing is a residential program for energy efficiency audits and installations, workforce education and training programs for youth, commercial energy improvements, public facilities for different agencies, codes and standards, that's what we're a part of, and then some financial programs that are going to launch next year. Our team is in Balance Green Consulting, and we are architects and green building consultants. And so we are celebrating just over 17 years in business as an organization. I'm here with Tatiana Soglin. I'm an architect and a lead accredited professional. Tatiana is also a lead accredited professional and a Green Point rated advisor. And so our firm does lead certification in green consulting and a lot of energy performance modeling. So hoping to be able to provide some information and answer questions along the way, but also hear your feedback throughout. The Codes and Standards program, for anyone who is kind of new to that program, we do have training like this one and in-person training as well. We'll do topics by request. If you have a group that you'd like us to be a part of, we'd be happy to jump in and help out. And we also provide specialized support services for jurisdictions in particular, and reference materials as needed. And then we have an energy code coach. So it's free. It's available to building departments, architects, designers, builders, project owners. And it's anyone in the territories who either practices in the territory or is out of the territory but has a project in that territory. You just simply fill out an easy online form, and we respond within a day or two. And it's the Energy Code and Cal Green. So questions about electric vehicle charging or any of those PERS raters, what kind of insulation, PVs, any of those types of things. We're happy to help out, and we can follow up with phone calls if needed. Here's our learning objectives for today about zero net carbon design, and it is worth an AIA Health Safety Welfare learning unit. And if you registered with your AIA number, we'll automatically get you the credit for that. And then you'll get a certificate. So if you're looking for licensure for a ZNCD, you'll get an hour and a half for that. And we do look to see that you've stayed on the majority of the time to be on the call. And the video recording and the slides will be provided at the end. So if any of these seem dense or you don't feel like you have to take a ton of notes, because we'll provide the slides. All right. Why the focus on zero net carbon design in the first place? California goals for energy resilience. So that's part of a bigger picture for being able to move away from carbon in our built environment and across the state overall. So that's addressing our climate impacts, which are obviously devastating and also very expensive. That's integrating into the building code. So wherever folks are standing on carbon and climate change, it's in the building code anyway, in terms of specific to carbon, and of course the energy efficiency and electrification, which we'll be talking about. Now they've required architecture licensure. You need 5 hours of ZNCD learning units to renew your license every 2 years. So a lot of folks are figuring out how to respond to that need in the market. And then ultimately, zero net carbon design will save money. It's healthier for the occupants inside the building, and it's more comfortable, and there is a resiliency, right? So as there are disruptions to the power grid, these were going to be spaces that are more resilient. So sources of carbon emissions, what's the plan? So what generates carbon emissions? Ultimately, the direct combustion of fossil fuels is our main source here. So that's fuels for transportation, it's fuels for industry, it's the direct burning of fossil fuels in our homes and businesses. So that's usually like hot water and furnaces. We're burning natural gas still for electricity, both in-state and imports. And then this kind of last category of other emissions, which is maybe agriculture, but it's also refrigerants. So that ties directly into the building industry as well. So the building industry, our sphere of influence is actually more than half of these components, because each of these pieces have some tied to a building, or even electric vehicles are now tied to the charging at buildings. So our shift from energy focus is really going towards carbon focus. Obviously they go together, but where you're getting your electricity in the first place makes a big difference. So here we're just seeing the carbon intensity of electricity generation, and we have that whole kind of first wave small, and then all the way up to solar PVs, which have a little higher production to make the things in the first place. But then natural gas, oil, coal are super impactful for the same amount of energy in terms of carbon. And so the good news is that California's energy grid is getting greener and is well on its way to a all clean power grid. So they update this data from the Energy Information Administration, is able to provide us month to month what the mix of our California energy grid has been for that month. And so July is the most recent one available, and natural gas was 32% of the grid. So all the rest of it is from non-fossil fuel sources. And about half of that, or half of the total, is solar and wind. So pretty exciting. Actually, when I checked in April, which is not as high an electricity demand month, it was only 25% of the grid's electricity was from natural gas. So there's a kind of a cycle depend on our mix of natural gas and what's available on the market as well. So what happens now is when the solar cannot meet the demand is that we have these natural gas peaker plants that kick in. So that's how we're riding out the waves. But as we transition to a clean energy grid, we're looking at other technologies that will be able to cycle out that peaker plant kind of process that we have now. So peak times of day, of course, are 4 p.m. to 9 p.m. And so solar with battery storage is a great way for us to be able to ride out the daytime, nighttime, as well as adding in wind into our grid as well. So this is a plant that was just completed in January of last year. And as you can see, huge solar array and a huge array of batteries as well, with kind of more on the way. So this is a great solution for us as we're going towards a clean grid. And so our emissions trends, so specifically looking at kind of dividing the pie slightly differently, is where are we, how are we trending? And so in terms of emissions, transportation going down, right? As we're doing electric vehicles and the vehicles are being charged with a cleaner grid. then that transportation goes down, industry, electric power generation as in terms of emissions. So these are all the trends one might imagine. With the one surprising one is that the high global warming potential is really the refrigerant. So that's very much building related. And California is addressing that as well. And we'll talk about that in a moment when we talk about heat pumps. And so how do buildings fit in? There's pretty natural path, actually. It's kind of good news. People have been doing this for a while. We try to have buildings that are super energy efficient, so are using energy as little as possible for all those functions that we need buildings to do. The energy that we do need, we make it all electric. We have on-site PVs and storage when we can. And then finally, we have materials, the construction process itself be low carbon. All right, so we'll jump into that first category, healthy, energy efficient buildings. So that's that operational carbon. But before I do that, Tatiana, any questions coming in, comments? Anybody want to raise the big picture hand about what they're looking for or seeing? No? All right. Okay. Okay, so first things first, we're going to consider the project size. I won't touch on this a whole lot other than to say things have been getting a lot bigger over time. So necessarily bigger is going to proportionally require more energy. So over the last 100 years, home sizes, it goes up and down a little bit. This trend chart just stops at 2016, and we know from more recent data that the home size is flattening, maybe coming down a little bit as we try to have some densification in our buildings. But we do kind of first things first is think about the project size. And climate analysis, super fundamental in terms of understanding one's climate zone and the implications of that. California is divided into 16 climate zones, and our energy code is tied to each of those zones. And they do an analysis to make sure that each of the requirements are going to be cost effective over the operational life of that building, 30 years or 50 years. And so those are good indicators about where investment is worthwhile. So in particular, in terms of taking advantage of your climate zone, if you have diurnal swings, so maybe it's hot during the day, but at least it's cool at night. And so you can kind of try to use that thermal battery of thermal mass. There's also trade-offs for heating or cooling. So maybe your project will be great in the winter, but then overheat in the summer or the other way around. So kind of just trying to hit that right balance. Thankfully, a lot of our design software now incorporates some kind of basic energy efficiency, performance, passive energy analysis. Although there's only very select softwares that can do the Title 24 energy modeling, but at least from kind of a design perspective, we have some good tools. And then finally, just recognizing and anticipating climate change, that we need to be ready for more extreme weather and also, potential fire conditions. One of our best tools is better insulation and better installation of that insulation. So here's a lovely clean installation where the bat insulation is tucked behind the power electrical box. It's all flush. It's going to touch all 6 sides once the drywall is on. We have some air sealing. This is actually fire foam that's around a window base. This is a blown in product that's going to fill the wall cavity, so we don't have gaps and voids and settling. Sealing down at the sill plate, and then having good R values, so the thickness, but also having a HERS verification for quality installation is kind of our baseline in our code, and it's just a really good idea. I think people are, if we are holding people to a better installation expectation, then that's where the market will go and the expectation, and that's what we'll be looking for, rather than stuff that shoved in or isn't done to a quality level. And air sealing is increasingly important. Also, testing to be done by HERS Rater. Side note that under the 2025 code, which starts in January, that they'll, instead of being called a HERS Rater, Home Energy Rating System, it was never a great name, honestly, and there's a whole different national program. Now it's going to be the ECC Energy Code Compliance Rater. So anyway, that person will come in and they can do a blower door test. So they put this fan in the door and close all the windows and put the home under pressure and see how quickly or slowly that pressure is lost. And so if you have it really well air sealed, it will keep that pressure in, which is also keeping in your heating or cooling that you want. So between the QII and the air sealing, those are some of our key metrics for both energy performance and, as it turns out, fire home hardening. So you just you get a lot better resistance to fire and smoke infiltration as well. Another key strategy is reducing thermal bridging, and this shows up in the energy code in terms of setting a baseline for having a continuous exterior insulation. This is a mock-up, this image on the left of a wall assembly. And so they show the stud framing, just a regular 2x stud framing, and then the structural sheathing. Then there's a self-adhered membrane. That's the weather-resistant barrier. The continuous exterior insulation, in this case, it's a Gutex, so a fiber-based product. And then there's this air gap, which is they call it a rain screen, although it's really just a moisture, it's kind of a vapor screen, as it were, so that that there's ways for the wall assemblies to dry out. And in this case, you can kind of see the installation here, and on the right, there's these plywood furring strips that's on top of the exterior insulation, and then this little ventilation gap. You can also use a mesh kind of product, or make this like a dimpled thing. So there's a few different ways to do that. But in fire country now, we also need to make sure that that venting is going to have that the vent itself at the bottom or at the top is going to have a fire resistance to it in the wildland urban interface areas, WUI. So that's kind of some of the basic construction envelope assembly. Shading still matters. So if you're, facing south and getting that awesome winter sun to passively heat your home, make sure that you also have overhangs, 2 to 3 feet, depending on how high the window is. If you have a lot of windows facing west, just be cautious, because that's our overheating period. You can do shades, but it has to go really deep, like 10 to 12 feet, in order to really block that the summer sun. And that's kind of in those shoulder months also, right? So really this time of year now is when that can really be impactful in the overheating. So movable shades works really well as well. And then thermal mass. So this is just kind of incorporated into our buildings in a lot of ways, because the drywall has thermal mass and we build a lot of slab on grade. But if you have a raised foundation, you can still add tile with a little bit of thermal mass. And that just helps with those stabilizing the interior temperature and that diurnal temperature swing. If you can cool that off at night, either with operable windows or some other kind of night vent cooling, then you'll be happier during the day, comfortable with less overheating during the day. So of course it needs to be right sized with the glass and where the glass is, and we can certainly talk about that a little bit more. The window size and placement in terms of daylighting. So again, these are all strategies that if there's no power at all, or just that little bit of energy that you need. So are we well daylit? And so in this case, daylight will reach into a room about 2 to 2.5 times the height of the window. So if you have a window that's 7 feet head height, doesn't really matter how low it goes. It's really the depth is based on how the head height, and so that'll go 14 to 17 feet into the room. So if it's deeper than that, you might think about clear stories that are kind of shown here in section. This kind of an old school design that I always appreciate, but in a more contemporary application, this is Mind Body in San Luis Obispo, and it's a kind of a big, almost warehousey kind of space, and they had all the windows kind of going up high, but they were all on the edge, and so we talked with them about moving some of the framing more central so that this clear story is maybe at a 1/3 point. So it did a few things. It brought daylight deeper into the other spaces, but it also created an architectural shift in ceiling heights and reduced the volume of the building that needed to be heated and cooled. And then avoid glare. So that's balanced daylight if you can. So if you have a whole bunch of windows on one side, maybe that gets the daylight in, but if it's not balanced, it's not comfortable for the eyes, and people will end up turning on the lights anyway. This is a hotel in Palm Springs. There's a clear story window on the back side. So the front side that's just out of the view of the photo is had a pretty big window wall into the interior courtyard, and they weren't planning on windows on the other wall because that's the sidewalk side. But by putting them up high, they were able to get that great balanced light where you go and you go, what a comfortable place. And they were still able to keep the privacy concerns and noise and any of those kinds of things. So, and then just being able to, adjust the light levels. If you do have plenty of daylight, you also want to make sure that there's ways to control that in terms of shading, awnings. Some people like blackout curtains, so that type of thing. One of the issues that we're finding, though, with the daylight and the window properties, and we are getting wonderful high performance windows, but sometimes if you have a really low solar heat gain coefficient, so it's a glazing property that rejects the heat gains, sometimes that impacts the visible light transmittance. And so like here's a kind of a glass schedule, a whole bunch of different options for low E coatings, U factors so the thermal heat transfer part is pretty consistent, but the solar heat gain coefficient, when it gets really low, visible light transmittance drops below 40%. And just as kind of a baseline there in LEED certification, if your visible light transmittance is below 40% or 0.4, then that doesn't count as a view. They're saying that's so shaded that you don't really connect with the outdoors and with nature to the same level. I mean, obviously that's a little bit subjective, but that's just kind of a caution as you look at high performance thermally energy wise that you are aware of what that does to you, visible light transmittance. Skylights and sun tubes, both have their role, I think. And sun tubes we used to do more of, I think. They're thermally almost invisible because they are so high performance. They're relatively small. And with that Fresnel type lens, they distribute daylight really evenly. And it's lovely, and it's almost like a light fixture. So in fact, it's so much almost like a light fixture that sometimes it doesn't really help people to connect with nature or even realize that that is a sun tube and not just an electric light. So they're great in some spaces, in kitchens and hallways and bathrooms, places that might be a little bit landlocked. But we also do tend to really like to use skylights, especially operable skylights, skylights that have the roller shades, skylights that maybe have sensors that will open depending on the CO2 level and close if there's rain. And so there's some really great uses of skylights. Interestingly, as we walk through all those strategies that are passive solar or just showing up in the energy code, that there's a great alignment with the passive house. And if you're here in person, I'd ask you to raise your hand, like who's familiar with passive house. And it's a program that came out of Germany. Actually, it was centered not on energy efficiency, but about health and comfort. And the basic premise is to have a very tight envelope, almost like a cooler or thermos or something. And so it's really great insulation. It doesn't do any of that thermal bridging. Air leakage is minimized, and it's performance based. So they make sure it's really tight. Quality windows, often you'll see like triple pane windows. And fresh air is introduced with a balanced ventilation system. So a heat recovery ventilator and usually some ducts or some strategically placed fans. So those are kind of the principles of passive house. It's also getting a lot of attention now, again, because they are doing really well in surviving, getting through fire because of these better assemblies. And then you partner those with all the other things that we talk about, energy efficiency and electric systems and solar and batteries and all of those kinds of things. All right, and then another aspect of energy efficiency that we don't talk about quite as much is the water, because there is this energy water nexus, right? So it takes a lot of energy to get our water, to treat our water after we've used it. And then we're using it in these kind of urban environments for outdoor water use, the landscape design, and then indoor, of course. And then in particular, heated water is kind of then the triple threat, as it were, that you're having to get the water, treat the water, and heat the water. So those are all some opportunities to be able to think about macro of reducing our water use, trying to have water that's more local and low carbon ways to heat our water. So these are just a couple of graphs to help us put some context around our water use in California. So this is the gray shaded area is the population of California increasing from 1960s to 2018 when this graph was done. The red line at the bottom is urban use. So that's or ornamental landscaping or schools, any of those kinds of, and our homes, all of those urban uses. The greenish one kind of towards the top is agriculture, and then of course total use. So what is fascinating is that as our population has increased, our water use overall really hasn't. So we've gotten smarter both in our urban water uses and our agriculture uses to be able to produce more and accommodate more people without increasing the actual water use. But it's the ratio in terms of water use to energy use is super different. So agriculture is actually, in terms of the water use of energy, agriculture uses hardly any energy to get that water, right? Because it's groundwater. They just need this slow pump to get it out of the well and then to let it dribble into the fields, or even just, a little bit of macro energy to be able to distribute it for overhead spray. But there's not treating it on the, we don't have to treat it on the way up. We don't have to treat it after the fact. It just is its own virtuous cycle when that works. It's an important resource we need to continue to preserve. And we talk about that a lot in other contexts in terms of groundwater and sustainable groundwater management. But in terms of energy use, agriculture is really not our issue. But you can see under this residential, the faucets, the showers, I mean, this is where we're really using a lot of energy and need to be conscious of that. So our reduction strategies, just job one, right? Half of that use at least is the outdoor water use. So being able to do native and adapted plant selections, high efficiency irrigation. California is kind of on a path of banning turf grass that needs that overhead. If it's being watered with potable water, there's a phasing out of those uses, right? So starting with kind of commercial properties, then going into HOAs and apartment buildings, not single family, that's not really on the docket, but we are moving away from grass. That's just for ornament. Rainwater catchment. We used to kind of poo-poo this a little bit because it was our rainy season in California is super compact, and you would need so many tanks. But now, as we use less water in our, we have less water demand because of our better plant selection and irrigation selection. A couple of rainwater tanks can get you maybe to July or August before you need to add any irrigation. So could be worth it. Recycled water is great because from a laundry to landscape system, it's year round. So you can get water all year to plant like maybe select trees or select areas. These are allowed by the plumbing code. You can go directly from your laundry or your showers or your bathroom sinks, not kitchen sinks, not toilets, of course, and not dishwashers. Those are all need to go to the sewer system or an engineered treatment system. It can go into your landscape. It can't go into overhead spray, but it can go under mulch or directly, like they make these little flower pot emitters for trees. And you can, of course, do commercial systems or municipal, purple pipe if you have that. Using efficient appliances, low flow plumbing fixtures, and then compact plumbing is a really good idea. And so what that means is that you want to cluster, and so you have to be on this like on day one as a designer to kind of figure that out, to put your water using fixtures, hot water using fixtures close to the water heater. And I'll spend just a second on this because this is a tiny home, and obviously tiny homes and ADUs in general are super popular in a good way. And so in this particular case, it's a small home. You can see the bathroom sink, the tub and shower, and the kitchen sink, and then across the way is washer dryer, which you think like, well, that's pretty compact. But here's the on-demand water heater outside. And what happened was that this on-demand water heater is too far to get to the hot water for the washing machine. And so it wouldn't be respond, and it's not allowed by energy code to use this particular water heater. And so they updated it by just swapping the stove and the washer dryer. And then that allowed, so all of these things are then closer to each other. So a little more efficient, and gave them some more options in terms of what kind of water heater they could do. In this case, electric resistance on demand. Any questions about energy efficiency so far? Anything coming up?
Nothing in the chat so far.
All right, great. We will keep going. Okay, so we kind of have this super efficient building. It's not using much water. We've got natural daylight. We've got all kinds of good things going on. We still need some heating and cooling and some hot water. And so let's talk about the efficient electric equipment. And the key to all electric is the heat pumps. And the beauty of a heat pump is that they don't make heat. Gas equipment makes heat, right? You light a you're burning gas, and then it's making heat, but heat pumps move them through the magic of refrigeration cycle, just like our refrigerators. This is the room temperature food into the refrigerator, And then that refrigeration cycle, the compressor, goes and takes that heat and dumps it out of the refrigerator, usually like at the little kick space at your feet, right? So it's the same technology in that in homes. You can cool. We've been using them, heat pumps for air conditioning for decades, right? But now we're also using them. Those magic things can work in reverse to actually do heat. So even if it's super cold outside, there's always a little bit of movement between those molecules. And so that will bring the heat from outside into the home. So we're transferring heat rather than making heat or cool, as we used to say. And so these heat pumps, we're seeing them all over the place. Of course, you can do a ducted system where you have the compressor that sits outside, and then it brings refrigerant line to a fan coil unit of some kind, or like a big air handler type of system. And then those are put into ducts, and just like you would have just a regular home with vents. And increasingly, we're also seeing, of course, these ductless systems. And in that case, they're visible, right? You see these wall-mounted units or kind of ceiling cassettes, could be a whole little base unit. They'll still have the compressor outside somewhere, but in this case, rather than having an air handler and ducts, you just go right to this ductless unit. There's also package systems. Those are pretty uniquely used for some retrofits, but generally hotels still have some as a kind of a window-based package unit. So that's the compressor and the air handler all in one thing. So here's the ductless mini split. You've got the head that we talked about. There's this refrigerant, this whole line set, and it kind of comes bundled, and it's got the copper tubing for the refrigerant, and it's insulated. And then there's this hose that's the condensate line. So just like your icy ice glass of water in the summer is going to drip condensate, the same thing's going to happen with the air conditioner. And so you want to make sure you have a place for the condensate to go. And then the power cord as well. So the electricity, the power to the head, the indoor unit, it comes from outside. So, and then these units can be wall mounted, they can be ground mounted. And yeah, so a bunch of different options there. They're super quiet now. I know that some people have been concerned that they're these kind of loud air conditioning units, but these are very quiet. Like a refrigerator. So not silent, but quiet. For water heaters now, we also, I think, especially in commercial settings, really everybody's just using heat pump systems for heating and cooling. It's cost effective, it's easy to install. So pretty willing market on the heat pumps for heating and cooling, and increasingly in homes as well. We're just having that ducted, ductless. The look, I think there's still an aesthetic look that we're talking about. In terms of heat pump water heaters, though, that is the new baseline for the energy code, and they're definitely more efficient, but they do need some different accommodations. It's not kind of the one-for-one swap with a water heater. So we'll take just a minute to talk about these heat pump water heaters. There's two main categories, these integrated kinds, where the heat pump is right on top of a tank. So that looks like a regular unit. And then there's also a split system option. Only a couple of manufacturers have these right now. So has a separate outdoor unit like the heating and cooling do. And then that is water is then plumbed, not refrigerant. Water is then plumbed to this tank, which is just a tank. It doesn't need power. It's just like a thermos. It's just really well insulated. So two different options for kind of the approach to water heater. If you're looking at these heat pump water heaters in with a little bit of detail, then you can see there's control panels. There's a condensate line, just like we talked about for the air conditioning, the tank itself. This one, you know, you have the refrigerant, it's sealed in, so you don't need like a special inspection for the refrigerant in one of these integrated units. And then the insulated hot water lines, of course. If for some reason the heat pump water heater is not getting the recovery, like if you have a huge crowd or you're doing just a ton of laundry that day, all the water heaters are have kind of a hybrid option with these electrical heating elements. So they will go to electric resistance heating if you need that extra boost, but that's really energy intensive. So you want to make sure that you have the thing performing as optimally as you can so that you're not relying on that electric heating elements. Oh, and a drain pan in the floor. Right. So when you're using these integrated systems, make sure that you understand that they are taller than the standard gas units, or even like an electric resistance water heater. Those really aren't allowed by code anymore. So your options were kind of gas, and you can still do gas. You need to pre-wire for electric. But if you do go to a heat pump water heater, or even if you're designing for gas, but you have to have it be electric ready, make sure you allow enough space. They're taller, and sometimes like the filter, air filter is on top. So you need access. So don't like sit a bunch of things on there, run conduit so close that you can't access the air filter. Be thoughtful about where you place these. We have had some folks concerned if an integrated heat pump water heater is like right next to your bedroom, just like you maybe wouldn't want a refrigerator right next to your bedroom, that kind of cycling on and off might be disruptive. Some are quieter than others, and they need a lot of air movement. So heat pumps for heating and cooling, those little compressor units are outside, so they get all the air they want. These tend to be in closets or garages. It works great in a garage, but if you try to put it in a closet, you need either a really big closet or louvered doors or ducts, like a vented duct kit. If you don't have that kind of opportunity, you could do the split system. This is what I have in my home. It's a Sanco brand, and so you have the you know, a compressor outside. In this case, this particular brand uses CO2 as a refrigerant, which is actually kind of one of the lowest ones, which is ironic, but most of the other refrigerants are way worse than CO2. So yeah, so insulated pipes for that. And so just as we kind of wrap up the heat pump conversation, that touching on the refrigerants is important. So just like remember when there are holes in the ozone and we all got together and said, oh, let's not do that anymore. That's what's happening now with refrigerants and trying to ban refrigerants that have this high global warming potential. So R410A was our go-to, and that was already better than a lot of the other ones, but now that's no longer allowed. And so 750 is the max of the global warming potential. So we're seeing a lot more of this R32 or R454B. I don't know. I'm seeing more of the R32, but maybe there's different ones. And then this R744, which is CO2. The names of the refrigerants, they're not sequential. They're not tied to GWP. I understand they may be tied to their chemical structure. So don't let the names of these refrigerants throw you off. So really it's the GWP that's important. And then there's other properties about how efficiently they operate, is there flammability, all those kinds of things. So anyway, we're on a path. And then, you know, the rest of your appliances, whether they're heat pump pool heaters, you can use heat pump instead of electric resistance or gas. Heat pumps, condensing dryers. Similarly, these need air movement to be able to function, and a little bit more time, right? A gas dryer is like, that's fast. So you have to adjust your schedule a little bit if you go to one of these condensing dryers. But once you get used to it, it's really not a problem in most settings, not every setting, right? So similarly, cooking, electric resistance cooking was and is super frustrating for a lot of people. Those coils, they take a long time to respond. People can get burned on them. Gas cooking is super responsive, but of course we're finding, especially in older homes, older cooktops, that there's a lot of combustion gases, and they're causing real health issues. So when possible, we're moving towards these induction cooktops. So these are magnetic, so there's magnets that are spinning, and those heat the cookware, and then the cookware heats the food. So this little demonstration on the left is showing that if you just stick the chocolate on the stovetop directly, nothing happens. But once you put the metal pan on there, then the pan will melt the chocolate, right? So they're very fast to respond and very efficient. I will say, I think it's a conversation. I don't want folks to feel like we're coming for their gas appliances. There's kind of a evolutionary draw that we have. And so I think, especially if you have an existing gas cooktop, and it's a relatively small carbon footprint, and if you love it, then feel free to keep that. On the other hand, if you're doing new construction, adding gas infrastructure just for a cooktop is really expensive. So we're seeing a lot more homes that are just all electric. It's just more efficient. It's safer in terms of fires and air quality, and so we're seeing a lot of that. And then in terms of electrification, of course, we have an increasing role in transportation. It used to be, and still in a lot of cases is, that people would go to a central place to fuel their transportation, right? But now our buildings are needing to accommodate electric vehicle charging at the buildings, whether it's homes, multifamily, commercial buildings. Sure, there are some central chargers at the, the mall or whatever, but a lot of infrastructure is now being put onto buildings, and that's in the California Green Building Code is requiring a lot of EV charging, which is a good thing, but it's just, again, another consideration as we are designing buildings. So we're going to talk about generating and storing electricity, but I'll pause for a moment, Tatiana, see if anything else came in.
Yeah, we had one question come in, kind of going back to insulation.
Sure.
What effect does moisture have on insulation life?
Yeah, so interesting. It's a great question because it depends on the insulation. So some insulations do better than others. So like a cellulose, mineral wool, those, any insulation you want to make sure has the capacity to dry out. But like fiberglass insulation tends to hold on to moisture, and so then there can be mold growth within that. So especially in if you do have an insulation type that's going to hold moisture, you really got to make sure that you're thoughtful about your membranes, because water often will seep in, which isn't the end of the world, as long as and I mean vapor, not like wet water. But if it does condense, if there's either thermal bridging that's causing condensation, or if just vapor goes through because of pressure, then you want to make sure that it could also, that the membrane is permeable to the outside. And that's when that rain screen or the vapor, that little gap comes into play to be able to help it. So obviously it doesn't insulate as well when it's wet, but worse is that it can grow mold. So yeah. Yeah, thank you. Great question. Okay, so a little bit on just adding solar for our buildings. Of course, we've talked about at the utility scale that's where California is going with our grid. But you can also, well, you can add PVs, and you're required to add PVs. So new homes, of course, require solar panels, and sometimes there's a goal. So this is just kind of order of magnitude, is that this first bay of solar panels maybe is about what might be required by code, and then you'd want to add more if you're trying for zero net energy design. So the code does not require you to offset all your electric grid with your PVs, because that's not the sweet spot on cost effectiveness. But if you are trying to go zero net energy and making that investment, you can add 40 to 60% more, depending on your electric use, and even more if you're charging an electric vehicle. And so in terms of scale here, so a new 2,000 square foot single family home in climate zone 4, say, would need 2.38 kilowatt system. And then just Jennifer, our principal certified energy analyst, just ran some PV requirements for the rural REN climate zones. And so you can see that there's a little bit of consistency here, 2 to 3 kilowatts of PVs are required, but you can see climate zone 13 is particularly high because that's a really hot climate, and they tend to need more air conditioning. And so that level of electric demand warrants a bigger PV array. So that is, again, it's a cost effectiveness that says if you're in a climate zone that's really hot, a larger PV array will pay for itself. Even if you're zero net energy, we tend to be grid tied, and we've been doing that for a long time. And it works out nicely in general, is that when you tie your, you generate more electricity during the summer, say, when we have long daylight hours, and then maybe we don't use as much electricity if we are, have our club, whatever. And then in the winter, we have shorter days, right? So if solar production is kind of peaks, then that zero net energy is really, we feed extra into the grid during the summer, and then we take more out during the winter. And over the course of that year, we zero it out. So that's kind of how grid tied solar systems, we use the grid almost like our own little personal battery. And 15, 20 years ago, the power company would pat us on the head and say, oh, that's fine, whatever. But now so many of us have solar that is making a real impact on the power company's ability to kind of manage the whole grid. And so they're really leaning on, California is really leaning on our projects. If you're going to add PVs, that you should also add your own personal battery, right? So here's where we're looking, this kind of majority of the Cal ISO is the independent systems operators. They're folks, have you seen them? They've got like 10 screens, and they're managing all of California's energy, where it's getting, what's getting fired up, where it's all going. It's an astonishing accomplishment. And so here's our mix. This was midday in April, so kind of that shoulder season. Little baseline of nuclear, geothermal, large hydro, right, is going to change during the rainy season. Gas kind of was dropping down, and then solar, just this huge impact. So we're having to manage it either with imports or with storage. So storage at that building scale can take all kinds of sizes, utility, commercial, multifamily, and then these private homes. And so if you are having PVs, they're basically saying under the current net energy metering pricing, it's going to work better to have battery storage. That'll be the most cost effective for you. Batteries are, there's a cost for sure. So, but it'll pay for itself at some point. We do need to be battery ready by code, even if it's not required. So do make sure that you have both the panel capacity and the conduit, but also enough wall space So that, because it has like all these different components to it. Disconnects, backup panels, load centers, inverters, etc. So here's one that's installed. In this case, they stacked it, and you can get the you can have like a little bit of a cover to it, and then to protect it from temperature extremes. You don't want like a whole bunch of direct light, but they can be outside if you want. And there's lots of home battery options. So we showed Tesla in that model, but there's all kinds of batteries now. So that's a good thing. And then this is an existing system. Hold on just one sec. Realities of working from home on a day, right? So this is actually our other principal, Jennifer's home install for an existing home. So again, kind of different financing options, other considerations, but this is just kind of breaking it down. So she got the stack, there's a stack of electrical panels, all the gear, the inverters, batteries, she got a new electrical sub panel, or a new panel with a sub panel and the controller. And so you have to think about, like in this case, are you needing re-roofing? If so, do your new roof first, of course. What's the additional cost for the panel upgrade? How much access do you have to for sun in the first place? And then what's your usage going to be? So here it is installed. She's plugging in her electric car. She's got the battery system, and then went with an electric dryer and electric cooktop. And so almost all the time, her solar and battery manage everything. But when the teenagers are all doing laundry on the same day, it's the one time that that she does have to pull more from the grid. But in general, her goal is to try to be invisible to the grid, because she's charging her battery during the day and then drawing off of that battery between that peak time of 4 and 9 p.m. Okay. So we're kind of progressing through. We got super energy efficient. We've got solar panels. We're all electric. We've got solar panels. We've got the batteries and the PVs. And now the last piece in trying to reduce our carbon footprint in the building sector is the materials, and that's the embodied carbon. So we focus all the time on operational carbon. How do we reduce the energy of operating a building? But there's this whole other sector of carbon that is used to make our buildings in the first place, and kind of dispose of it at the end of its useful life as well. And so that's called embodied carbon. And it kind of went down because 20 years ago, in a typical building, the big green section of pie there is the operational carbon, and embodied carbon was just relative to operational carbon, a lot smaller. So now we're making our operational carbon footprint so little to get to that whole zero net carbon design operationally, that now embodied carbon becomes more significant. And it's significant not only because of just its carbon footprint, but also because of the time value of carbon. So if you think about a building's lifetime over 100 years, cumulatively, operational carbon will increase, year 1, year 2, year 3, you're like, okay, there's a little bit. But the embodied carbon is all impacted during construction, and now is the moment when we are super concerned about that carbon. So if we can, there's a growing sense of urgency to address the embodied carbon in the first place. And with that, I will turn it over to Tatiana to share a little bit more about carbon footprint.
Thanks, Andy. So during the 2024 Cal Green intervening code cycle update that went into effect on July 1st of last year, embodied carbon was added as part of the Cal Green mandatory measures for non-residential projects. And currently the non-res projects 100,000 square feet or more, or schools under jurisdiction of DSA at least 50,000 square feet are required to meet one of these three pathways. And when the 2025 code goes into effect on January 1st of 2026, the threshold for all non-residential projects will drop to 50,000 square feet. So over time, we'll see embodied carbon requirements starting to apply to more and more projects. So this is a quick overview of the three pathways. The first is building reuse. So this applies to existing and additions and alterations only if the addition is less than 2 times the area of the existing building. For this, 45% of the structure and enclosure must be reused. The whole building life cycle analysis requires modeling software to show a 10% reduction in embodied carbon in primary and secondary structural elements from a baseline. And then the prescriptive method, for this one, the code sets global warming potential limits based on industry-wide standards for specific materials. Currently, the Cal Green mandatory measure requires those materials to be 175% of the industry-wide Environmental Product Declaration global warming potential limits. That's a mouthful. If you're familiar with Cal Green, you'll know that mandatory is required, but the tiers listed below are also sometimes required by certain jurisdictions as part of a REACH code. So you may have seen a graphic like this before that breaks down the life cycle of products, and this is the framework that we use to understand where you find embodied carbon in the construction process. So first is the product stage, A1 through A3, construction stage, A4 through 5, use, B1 through 7, end of life, C1 through 4, and beyond the building life cycle stage D. Each of these stages is broken down into processes, like for the product stage, there's extraction, transportation, and manufacturing. Under the use stage, we can see that operational carbon impact has its own stages outside of the embodied carbon impact. Again, that's what we're more used to thinking about when we think about carbon emissions from operational energy and operational water, which we spent a little time talking about earlier. And when looking at data for product selection, you're mostly looking at information covering stages A1 through 5, so that product and construction stage. Whole building life cycle assessment expands that to look through stage C, and then A through D looks at going beyond the life cycle of the building, thinking about things like reuse and recycling. So this slide here shows the relative size of emissions broken down by stage. We can see that the vast majority of embodied carbon emissions come from that product stage, again, including raw materials, extraction, transportation, and manufacturing. And most environmental product declarations report emissions in that stage. So we have a pretty good data set on emissions in that range that helps with product selection. And we can see what has a bigger impact on embodied carbon. And for some materials such as concrete, which we'll talk a little bit more about later, as much as 90% of embodied carbon emissions can be from just that product stage. So, in conversations about reducing project operational emissions, first the focus is on energy efficiency to reduce overall energy demands. Then to address the remaining energy use, renewable energy is specified. And you can take a similar approach with reducing carbon emissions. So here, energy efficiency is a parallel to material efficiency and should be done early in the project to reduce the total amount of material used. Then to address the embodied carbon in the remaining materials, low carbon material specifications are used. So low carbon specs will get us part of the way, but we can make real gains using less materials in the first place. So I say that the greenest building is the one that never gets built. So that would be considered 100% reduction, but not very practical. So the next strategy with the next biggest potential for reductions is material reduction, using less stuff, reuse, being clever with structural configurations, being efficient with space and carbon intensity, and finally minimize. Only after this work has been done do low carbon specifications have their day. We saw early that low carbon concrete might help a project realize on the order of 9 to 16% reductions. For comparison, it's estimated that reducing structural spans or shape optimizing reinforced concrete floors can result in up to 70% and 79% reductions, respectively. So concrete is the product most commonly discussed when it comes to embodied carbon because it has such a high impact. Concrete is composed of aggregate and binder, and Portland cement, the binder that is used the vast majority of the time, is responsible for over 90% of concrete's emissions. And nearly 70 or 95% of cement's emissions come from clinker, which accounts for 91.4% of the material substance of cement. Clinker is produced by heating limestone and clay to over 1400 degrees Celsius, which precipitates a chemical reaction called calcination. The energy emissions from heating the kilns accounts for 35% of concrete's emissions, and the calcination process releases CO2 in great amounts, resulting in 53% of concrete's emissions. So, in summary, the production of concrete is very energy intensive, and there's a lot of greenhouse gas emissions associated. Some specific ways to approach use less stuff are laid out here by the Carbon Leadership Forum. If you take a baseline building, they show how to stack reductions in steps towards an optimized design, specifically first looking at optimizing design loadings and reducing spans. This would inform and be informed by structural material selection. The second graph shows the relative global warming potential for different structural materials and systems, and then consider material changes and low carbon specifications. So now looking at a few high impact material strategies for cost-effective low carbon product specification, starting with concrete. Again, we know that has a really high embodied carbon reduction potential at no to low cost premium. So for this one, substituting cement with alternative cementitious materials. Rebar and structural steel can have up to 10% reduction by prioritizing recycled content. Insulation also has a significant potential for reduction using things like cellulose or mineral wool bat installation instead of foam. We'll take another look at some other alternatives later on. Glazing is an interesting one. It can come at a bit more of a cost premium, but there's still some options to consider, like using low carbon window frame materials and then using no more than 2 panes of glazing. When we're thinking about the window glazing, it's important to consider the trade-offs. When you have more window panes, you get better window performance, and you're reducing operational carbon, but you'll have more embodied carbon associated because you're using more materials. And then last is finished materials. No to low cost premium. For this, look at using low carbon or durable materials that don't need to be replaced as often. So thinking about things like material reuse or designing for deconstruction and future reuse. So to find how much embodied carbon is in a product, you'll look for the Environmental Product Declaration, or EPD. It'll look something like this. Each product is evaluated across various categories of its life cycle. For example, stages A1 through 5, which includes, again, that product and construction stage we were looking at earlier. The EPDs have a variety of metrics for assessing environmental impact, but we're just focusing on the global warming potential, or GWP. So you'll see this one, it's listed as the very first metric on the document. In this case, you'll see it broken down a little further by life cycle stage. So when you're comparing different products, different EPDs, for accuracy, you'll just want to make sure that you're making comparisons with the same metric across the same life cycle stage. So materials that sequester carbon can also have a dramatic impact on a project's embodied carbon footprint. This graphic is showing two different design options for the same building, the first with a concrete design and the other with a mass timber design. These lines are showing the cumulative embodied carbon over the life of the project. And because, again, concrete has a lot of embodied emissions from production or manufacturing, we're starting out the project with much higher emissions. In comparison with mass timber, because trees draw down or sequester carbon from the atmosphere as they grow, the timber design is negative, or net sequestering carbon. And as the project progresses, the embodied carbon goes up through transport, construction, service life, and end of life. But we can see that over time, the timber project still remains net negative. And this example is looking at trees, but there are many other sequestering materials. So, looking at this slide here showing insulation, we can see there are many different types of insulation, and not all insulation works for all conditions, but where substitution is feasible, charts like this can be a good guide to kind of determine what products could be used. So the numbers here are for a particular R value. And so for this, you can see that petroleum-based products are emitting more carbon, and then at the bottom there, things like cellulose, hempcrete, and straw bale are sequestering. And this is just a quick list of a few products. There's a lot of emerging technologies also that are being developed, things like mycelium board from mushrooms. There's expanded cork. There's a lot of different materials that can be used for insulation. So again, depending on what kind of insulation you're using, you can use things like this and EPDs to determine where swaps can be made.
It's interesting too, is that we're also seeing kind of some mix and match opportunities depending on the application. So for example, if you're doing an unvented attic or an unvented cathedral ceiling, then the closed cell spray foam is an effective way to get an air barrier, because 2 inches of that foam. But it used to be that, and some still do, is that you would get your entire R value. So you might do, 6 inches of that spray foam in order to get your R value. What we have a lot of builders doing is they call it a flash and pack. So you just do the 2 inches that are required to get the air barrier, and then you go in with a cellulose or other kind of a bat type of insulation that's going to be able to, you could even do regular wool. So cotton, any of those kinds of products, so that you're getting as much of the sequestering product, but still understanding the realities of trying to design for energy and fire protection. All right. Well, and with that, thank you, Tatiana. And to wrap this up is just to note that California is taking steps to reduce carbon emissions across all sectors. And buildings have a really big role in that reduction, and that there's tangible, often code required ways to get there. So some of it's the right thing to do, and some of it you just have to, it also is required by code. And the strategies are pretty straightforward in the sense of have a very energy efficient building, have it be all electric, tied to our clean energy grid, generate PVs, have PVs to generate your clean electricity on site, use storage in order to ride out that that seasonal and daily swings of how we make our energy. And then finally, make sure that to the extent possible that you're thoughtful about low carbon materials, both upfront design to reduce those materials, be efficient with materials in the first place, and then select low carbon materials. And that is what we wanted to talk to you about today. So before we let you go, and we will go ahead and open it up to questions in just a moment, as a reminder, please do visit the ccrren.org website. You will get a copy of these slides, so any of the links will be on there. Codes and Standards program you could go to, and then on that page, you'll see there's a Energy Code Coach, and that has an intake form, and you just fill in, very quick, simple form that just helps us to be able to track it and make sure that we're getting back to you. And again, it's on Energy Code or Cal Green. So either one, we're happy to help sort through any of your questions. We do have, we're kind of rounding out the 2025 calendar here. So in November, we do have a class coming up on heat pump water heaters in the 2025 Energy Code. So get a little bit more into the details on that we touched on briefly today. We just had a couple classes this fall, and they are available on demand. So one is Energy Code for ADUs, and another is leveraging the Energy Code for home hardening. So that's that interface between the Energy Code and being, you know, a WUI fire resistant kind of construction, and that those two things generally play nicely together and work with each other, although there's a few exceptions to the Energy Code to meet the WUI code. We are going to launch a quick poll. So if you could do us a favor and give us your feedback, that also helps with our reporting. And if you'll also get a report, if you have any questions or other feedback, that will also be in that email that you get at the end. And like I say, you'll automatically get your certificate for ZNCD, but if you do have any questions about that, just go ahead and write to that codes group. Okay. And with that, I'm going to stop sharing screen and see if folks have any questions, comments. This is always a great time for people to share if they have observations, things that they've been seeing either as problematic or successful in terms of any of the things that we've been talking about. Appreciate the positive feedback. All right. I do think the zero net carbon design, I think the materials I think are pretty interesting, and it'll be really interesting that concrete in particular, just what kind of, there's so much great research coming on in terms of concrete that not only doesn't have that big carbon footprint, but maybe even sequesters carbon on its own. I mean, it's the #1 building material across the planet. So a lot of people are really interested in doing research and doing more how to bring it to industry to scale, you know, so that's cost effective, locally based, right? So we actually have a local builder who's doing a permitted Adobe home. So he's making the clay adobe bricks right on site using locally sourced clays, and it's not cementitious. So that's pretty cool. And yeah, I don't know if I'll catch on again. All right. Well, I'm not seeing any more questions come on. So let's see, here's one about if natural fibers are used in fiberglass, what about carbon emissions? Right. So I think that's a great question in terms of fiberglass is way less impactful than foams, those fossil fuel based foams or petroleum based foams. Fiberglass necessarily isn't a carbon sequestering material, right? Because it didn't grow. But it is, there are some really good fiberglass products that are also using recycled content. So that's a good way to reduce the footprint. And then also that are, just a super affordable option. There's also installations that are using like wood fibers, like we talked about that rigid one. There's also ones that are more of the fat format. Yeah, and feel free to unmute if you want to, make a comment or ask a question online. We always try to wing it on the answers. So, yeah, good question. All right. Great. Well, we'll give you 5 minutes of your life back, and I hope you have a terrific day, and look for those materials in your inbox. All right. Thanks, everyone.
Thanks, y'all. Have a good day.
Thank you.